Okay. All right, so I wanted to go over solving systems by graphing. This is covered in section 10.1, and we're going to use technology to do it because, well, graphing by hand, it's kind of tedious, and then especially when you're solving, if you have an error in your graph, then your answer is going to be wrong. So I did this because I thought it'd be good to show you guys the technology, and I already have a video on solving by substitution and elimination, which is how we solve algebraically. And that is actually the preferred way, because when you solve by graphing, you have to inherently round your answers. So you generally don't want to solve by graphing unless it's like a real world problem, because that's where you're allowed to round. So just to start off, so we're solving systems, and a system is two or more equations that we're taking together to find a solution that works in every equation there. So if there's two equations, our solution has to work in both equations. And these equations have x and y. So our solution is an ordered pair, x and y. And because these are x and y, these are things that we can graph. And if you graph your equations, then the solution is where these equations intersect. The general rule is that the number of variables you have is the number of equations you need in order to solve and get a single answer. So like when we solve an equation for x, if x is our only variable, you only need one equation. But if you have x and y, in order to get a single answer, you need two equations because you have two variables. So if we have two equations, two variables, we can get a single answer, which is an ordered pair, one number for x, one number for y. So there are different types of solutions, and we're looking at just linear systems where we're just graphing lines. If you have to go on to pre-calc, you'll look at other types of systems where you'll have like things with quadratics and all the other types of equations we looked at. But solutions to linear systems are very helpful when you think about it graphically, because it gives you an idea of what it means. So we get one solution when our two lines intersect, because they cross each other. There's one point where they intersect. And because we're looking at linear equations, so that's y equals mx plus b, the only way for two lines to intersect is if they have different slopes. So if you have two equations and they're both in slope-intercept form, just looking and determining what the slopes of those lines are can tell you if there's going to be a solution or not. So if the slopes are not equal, you know there's going to be a single solution to that system. And we have a special name for these, which are consistent systems. They're called consistent because there is a solution. And then they have independent equations because there's two different equations. Now, we can also potentially get infinite many solutions or no solution. So if you get infinite many solutions, that is when you have two equations, but when you graph them, they give you the same line. So the equations may look different, but graphing actually gives you an identical line, so the lines are on top of each other. So in that case, they're basically intersecting everywhere, which is why there are infinite many solutions. So an example would be like if I had y equals 3x plus 5, and then my second equation was 2y equals 6x plus 10. It's just the first equation times 2. It's still equal to the first equation if I solve for y. So if you graphed both of those, the equations look different, but they're actually the same line, and so you just have one line there. So the slopes of these lines will be equal, and they'll also have the same y-intercept because they are identical lines when you solve for y. So these systems we call consistent because they're still solutions, but they're dependent because the equations are identical. They're basically, you have one equation overall when you boil it down. If you solve one equation, you get to the other. So there's just one equation, two variables. And so your answer to like whatever your variable is for y depends on what you plug in for x, hence called a dependent they have dependent equations. Then the other possibility is when we have no solution. And this is when your lines are parallel. So like if I just graphically, one solution, they have some intersection. Infinite many solutions, they're just on top of each other. And then no solution, they're parallel lines. Because if they're parallel, they're never going to cross each other. So there's no place for them to intersect. You're not going to have a solution. And this is why it was so, we learned how to determine if lines are parallel. So if for parallel lines, their slopes are the same, but the y-intercepts are different. So that's the difference between infinite many solutions and no solution, is looking at those y-intercepts, because they both have the same slope. So if the y-intercept is different, that means there's no solution. And so then you automatically know, okay, there's no solution in this system. So if you're solving systems, if you have your equations in slope-intercept form, you can use this information to determine how many solutions there are without even solving. And that can save you some time. Like if you realize, oh wait, these are going to give me infinite many solutions or no solutions, then it's not worth solving, because you're not going to get a single answer. So it's just a kind of a check, and it just kind of gives you a visual of what your solutions mean. So when we have something with no solution, we called it inconsistent system because there's no solution, but we do have independent equations because the equations are different. So this is sort of overall, what it means to have solutions. Really think of them in graphical terms, especially in the real world situation, because that will really help you understand what do these numbers mean that I'm solving. So the most common there are lots of applications for systems of equations, tons of applications. They're used all the time in business. They're used all the time in computing, and anything where you're doing like data mining, used a lot. It's anything that you do have to do something on a computer, you're probably dealing with a system somewhere. Like even people in computer programming, they will be dealing with systems, or at least matrices, which is a form of a system, or arrays where you have to program data tables. I mean, even Excel, in some aspect, you can kind of think of as a type of matrix, and a matrix is a type of system. So it kind of all goes back to systems of equations. But the ones that we generally solve by graphing are those that are things like supply and demand, because you'll have curves that you'll be looking at, and you want to find, well, where's the equilibrium price of the supply equals the demand? Or cost and revenue, where are you breaking even where your cost equals the money you're making? Or wages, maybe if you're comparing different salaries, or maybe you're given a flat rate, like you're going to make this much a week, but then there's another job and it has an hourly wage, and you're trying to figure out, well, what is the best one for me? You might want to solve these by graphing, because when you're looking at these graphically, you can see, okay, where are we intersecting, but then where is one better than the other, because maybe it's higher, the graph is higher than the other graph. Or where am I like losing money because the graph is below the other graph? So a lot of business stuff actually ends up being solved by graphing. Other applications that we do, we tend to actually solve algebraically without a graph, because they don't make sense to graph. Like you can have systems of equations where you're trying to figure out, a common example is mixtures. Like if you're mixing oil with water, and you're just trying to figure, you want like your solution to be like 15% oil or something like that. Those things don't really make sense to graph, because like you're dealing with percentages. It's not like you're looking at how things are moving over time. So those we usually solve algebraically, not graphically, because it just doesn't make sense to look at it as a graph. So I'm going to do examples of basically all three of these. And I'm picking word problems because when you're graphing, you have to round. And when you round, that's what happens when you have word problems. When you have a word problem, we're not usually looking for an exact thing, or we're allowed to round. So we're just going to do 3 different word problems, one for each of these. We'll use Desmos, but we'll go through the whole process so you can see really how these are used, especially if you happen to be going into some sort of, if you're going into business, this would be really helpful. But even if you're not going into business, understanding this can be really helpful. So first one, this is coming from section 10.2. It's problem number 67. So a cleaning company charges $100 for each office it cleans. The fixed monthly cost of $480 for the company includes telephone service and the depreciation on cleaning equipment and a van. So this is a cleaning company, they're making $100, but then they also have to pay for their own supplies, the phones for people to call them, the equipment, all of that. The variable cost is $52 per office, and that includes labor, gasoline, and cleaning supplies. So this is really relevant to anybody who may be starting a business, or even if you're not starting a business, if you're just doing something on the side, this could be a really useful kind of equation or system here. So part A says to write a linear cost function. So linear, so we're going to write an equation of a line. Cost function, so we're writing it just for the costs, representing the cost C of X. So the C of X is telling us what variables that we're using. So for part A, our cost equation is going to be C of X equals something. X is going to be our input value. C, we're using C for cost. And then it says it's in dollars, so it's telling us what units we're using here. So we're writing a linear cost function representing the cost C of X in dollars to the company to clean X offices per month. So we're writing an equation that we can use to determine what our costs are. So we have a fixed monthly cost of $480. So for sure, we know that we have $480 for our costs. But that's fixed. It does not depend on how many offices we're cleaning, so we don't have to involve X with that at all. But there's additional things we have to pay for, so that means we have to add them on, and that's the variable cost. So it costs us $52 per office. So if you take the cost per office and multiply it by the number of offices, that will give you the total that you have for however many offices you cleaned. So we represent that as 52 times X, or 52X. And then this is a linear equation in slope-intercept form. We just kind of flipped the order based off of the information that we're given. And you can always check yourself by looking at the units. 480 is in dollars. And then 52 is dollars per office. And we're multiplying it by X, which is the number of offices. So you can see that that will cancel out our units of office. And so we're just adding dollar amounts together, which is what we want to get a total amount in dollars. Are there any questions on that equation? Okay. Now, part B, write a linear revenue function representing the revenue R of X. So R just stands for revenue. Again, this is going to be using slope-intercept form because it says linear. For cleaning X offices per month. So this is the money we're bringing in. This is different from profit. Profit is the difference between cost and revenue. Revenue is purely the money you're bringing in before you subtract out the cost. So we're not subtracting out costs or anything. This is just based off of what we charge for income or for per office. So if there's $100 for each office, so that would be 100 times the number of offices we're cleaning. 2 offices, you get $200. 5 offices, you get $500. So it's just 100 times X. So those are parts A and B. And if we were to actually write these as a system, the official way that we write the system in mathematics is that we have this curly brace, and then we write our equations on top of each other to the right of the curly brace. This is how we write it mathematically. just make sure the curly brace is surrounding both equations to show that they're being taken together. So that's our system, and that's what we're going to be solving by graphing. So part C says to determine the number of offices to be cleaned per month for the company to break even. So the break even point this is where your cost equals your revenue, or where your two equations are equal, where C of X is equal to R of X. And graphically, that is our intersection point. So in order to determine this number, and we're going to do this by graphing, we're going to bring up decimals. So I need to go to the graphing calculator here. Okay, so I've got my graphing calculator open, and so I'm just going to click here, and I'm going to type exactly what I see with the function notation. So you just type exactly what it gives you. C of X equals 480 plus 52X. And so now we've got some line. And then I'm going to type in my next one, R of X equals 100X. So when you're solving graphically, you're trying to find where they intersect. And right now they're not crossing anywhere. So we have to adjust our graph. So I just recommend using the zoom out tool until we can see where they intersect. And so we got to a point where they're intersecting somewhere in here, but we can't really see it. So we need to adjust our graph here so we can see this better. So I'm going to go to graph settings. And I'm going to change my x-axis because my x-axis right now is going basically from negative 1200 to 1200, and that's too much. I only need to see like this little small section here. And so like if I did negative 100, that would give me here, that's negative 50. So maybe we just want to do from like negative 50 to 50 here. So I'm going to just type that in, negative 50 and 50. Okay. And so you can see now by adjusting that, we can see where they intersect, and then you can click and drag so that you can center at that point. So this is the intersection point, and when you're doing it graphically, you're basically reading the graph and then reading what that ordered pair is. So it looks to me that it's 10, 1000 based off of our ordered pairs here. So I'm going to just go back to my slide here, and I'm actually going to go on to continued. So our ordered pair appears to be 10, 1000. And we need to know what that means. What does that ordered pair mean? So this is X and Y. X is our input. And you can go back to the problem. X is the number of offices that we're cleaning per month. So that is number of offices here. And then the 1000 is just the dollars. And that is the cost is $1,000, but the revenue is also $1,000 because that's where they break even, where you're spending as much as you're bringing in. So part C says determine the number of offices to be cleaned per month for the company to break even. So to break even, we need to clean 10 offices a month. So when we have a solution to an order or to a word problem, we always want to write our answer in words. So we'd be writing this out. To break even, we need to clean 10 offices per month. And you can see how this would be really helpful if somebody's running a business, because that gives you an idea of, you know, you want to have some idea of how much work you need to do in order to start making money, or at least to break even. Because if you had no idea how many offices and you just started this business and you did 2 offices, you'd be losing money. So coming up with an equation for your costs, what you're bringing in, can help you to determine how much business you need to do in order to be successful. And it can also help you determine if, okay, let's say I can't do 10 offices a month, I can only do 5, maybe I need to increase my price of the cleaning in order to make up the difference. So you can kind of adjust your equations as needed based off of this information. So it's really, really helpful. And then part D says, if 28 offices are cleaned, will a company make money or lose money? So to answer part D, we can go back to our graph. So 28 offices is going to be somewhere around here. And so we can't really see what we're looking at here. So I'm going to move it. So 28. So we hit the red one first, and then the blue one is above it. So red here is our cost. I wish I could like label the lines, but I can't. So red is cost, blue is revenue. So the cost for about 28 would be under 2,000. I'm just kind of estimating here, but the revenue is much higher, way higher. It looks like $2,800. So you'd be bringing in more money than you would be spending, because your spending is down here, your income is up here. So you'd be making money because your revenue is higher than your cost here, because it's above the line. So for 28 offices, you'd be making a lot of money based off of our graph here. So part D, if we clean 28 offices a month, let me review, will a company make money or lose money? The company will make money. So you can see that this is very useful. Systems equations are very, very useful, because it's something that businesses look at a lot. And it's helpful for your own budget too, is you can use it to budget. This is my income that I'm going to be making throughout the year, and then this is what my costs are going to be per month, and you can kind of see, are those going to line up? Am I spending more than I'm bringing in? That sort of thing. Are there any questions? Okay, so that's the first example. That is sort of a cost versus revenue example. Second example here, also from 10.2, this is problem number 69, and this is a supply and demand kind of thing. So this is something that economists look at a lot. And I know sometimes people say, I don't know where I'm going to need graphing in my life. Maybe it's not going to be useful. Even if you are not personally going to be graphing, solving these systems, having an understanding of what these graphs mean, like if you're reading an article and they're showing graphs of 2 different things at the same time, or if you have 2 different graphs, trying to put them together visually so that you can compare them and really see, okay, is there overlap here? Where do they intersect? Just being able to interpret these problems graphically and what it means is a good skill. Even if you're not going to be doing this in your daily life, it just helps you understand what's presented to you, any data that you get, anything you see on the news or that you're reading about. One common graph that we see could be like, we've been seeing graphs all over with COVID, but there will be where it will graph, like you'll see a graph and it'll graph different countries on the same axis. And you can even see, okay, where are the COVID cases equal? Where do we have the same number of COVID cases for each country or something? You can look for intersections there, or at least being able to understand what it means when they cross. So most of us are not going to be making supply and demand curves. Those are really something that economists really worry about, but some people in higher level business, they might be, hire people to do this for them. So suppose that the price P in dollars of theater tickets is influenced by the number of tickets X offered by the theater and demand by consumers. And this is very common. If you have something that's priced too high, people are not going to want it. But if it's priced too low, demand's going to be really high because it's going to be so cheap. So you're trying to balance your supply and demand to get a good amount of price so that you can supply as much as you have while still making sure you don't run out, like you don't have enough, which is like if we think about what happened last year at the beginning of the pandemic, demand outpaced supply. And we ran into problems where we didn't have enough toilet paper and cleaning supplies and all that kind of thing. And then you've also got problems where supply is too much for demand, like planes. We have lots of planes right now, but nobody's flying them. So the supply is higher than the demand for them because nobody's going anywhere. So with supply and demand, you're trying to balance these out so that you're not losing out on the opportunity to make more money because you don't have enough items, but you're also not losing money because you have things sitting and not selling. So in this case, we're given the equations already. We can interpret what these equations mean. Our supply says P equals 0.025x, and this is measured in dollars. X is the number of tickets. So this is just saying that the cost of, or the price of supplying tickets is $0.025. Like that's a little under 3 cents. And then we've got demand. Again, this is in price. It's negative 0.05x plus 104. That negative is telling us that the demand goes down as there are more tickets available. And then it just starts out at 104. So like that 104 is just where you start off if you had no tickets. That's like your base price. And then your price decreases as you have more tickets available because we've got that negative slope. And we understand negative slope means as your X gets bigger, your Y is getting smaller. So these equations, we get an idea of kind of how they're working. So part A says to solve the system of equations defined by the supply and demand models. So we're going to solve these by graphing. So we're going to literally graph these two equations. So I'm going to pull up, Desmos again, and I'm going to just clear these, and then I've got these written down so that I don't have to keep going back to my other screen. Okay, so these are our two equations, and now you can see that we've got green and purple here. And again, we're not really seeing where the intersection point is. So first I'm going to click and drag, and then I'm going to kind of, if you zoom out, we're trying to figure out where they might intersect. It's getting closer. They're getting closer together as we get over here. So the intersection point looks to be somewhere over here. And then it's getting pretty close. So I'm going to start just zooming in. This is the problem with graphing sometimes, is that you have to kind of figure out where is it and find it on your graph. So it looks like they're crossing somewhere around here. Purple's on top. Is there a spot where green goes on top? Because that's where they switch. Okay, we're getting closer to it. I'm going to zoom in some more. Okay, green is somewhere getting on top here. Okay, so it's somewhere right now. It just looks very flat. We have to kind of adjust. So I am going to change my graph settings. I'm going to make my y-axis smaller because you can see that our y, we have a lot of extra stuff on our y that we don't need to see here. So I'm going to adjust the y this time. And I'm going to say we're going to go from negative 50 to 50 because that will kind of make sure we're centered around where this is. So instead of changing X, I'm going to be changing Y. And then hopefully we can zero in on where they cross. So you can see, okay, we can see a little bit better here. So I'm going to zoom in and keep zooming in. And we might have to keep adjusting our y. So maybe I'm going to do negative 39 to 40. Negative 39, positive 39, 39 to 40. Okay, so we're up. Okay, so now you can see I'm adjusting my y and I'm kind of getting a better idea of where this intersection point is. But you can see that we have to do a lot of adjustments here, and this is one of the downsides of graphing, which is why we have these other methods, substitution and elimination, because doing this by graphing, it's nice if the graph looks really nice, but when you have things that are really close together like this, it's really difficult to find that intersection point. So I'm going to just be like basically adjusting this. Okay, I just adjusted my y slightly, so now you can see kind of where the intersection is. It looks like it's right about here. So that looks like it's at 40 on the y, but we got to figure out, well, where is the x? Now, luckily for us, Desmos labels the x even if we can't really see it. So that's at 1600 here. Now, can you imagine trying to graph this by hand and finding this point? Like, you would not want to graph these equations by hand and try to figure that out. That would be insane. It wouldn't be, because you would graph probably from like negative 10 to 10, and then you wouldn't be able to find this point. So this is where technology is really helpful, but it's also kind of annoying and why we solve with these other methods. But according to graph, it looks like 1640 is our ordered pair. So the intersection is about 1640. So when it says solve the system of equations defined by the supply and demand models, that's saying it's looking for that ordered pair. So that's what it's looking for here. When it just says solve, you don't have to put it necessarily in a word like or in a sentence, because it's just saying solve the equations. It's not saying find the equilibrium price. It says find the equilibrium price or find the equilibrium quantity. That's where you have to put it in words, because it's actually giving you some context here. But here it just says solve the equation. So it's just 1640. Part B and C are where we interpret these ordered pairs to give them context. So B, what is the equilibrium price? So we have to figure out, okay, what's our input and what is our output here? So our input X is the number of tickets, which means that our output here is price. So for part B, the equilibrium price is, and then we've got 40, and that's in dollars. So it is $40. And then part C, what is the equilibrium quantity? Or that's how many, quantity is how many. So how many tickets to get to equilibrium? The equilibrium quantity is 1600 tickets. So this is basically saying that if we want to balance out the supply with the demand, we should price our tickets at about $40, and then we should expect to sell about 1600 tickets for this theater. That's sort of where it's at equilibrium, where the supply and the demand is going to be equal. So if you want to expect to sell 1600 tickets to meet the demand, you want to make sure you have 1600 tickets available, that you have the supply. And so in a situation like this, you probably can't fit 1600 people in a theater, and that's why you would have multiple showings. You'd want to make sure you figure out how many showings that you would need in order to fit that number of tickets. If your theater only fits 500 people, you'd have to take your 1600, divide by 500, That gives me 3.2. So in order to make sure you meet the demand for 600 tickets, you would need to have at least 3 showings. You'd probably have 4. So that way you have a little bit extra, but that would make sure that you have enough showings that you can sell that many tickets, because you're constrained in your theater with how many you can have at one time. So you can see that this is very useful once you understand how the supply and demand works. That can help you schedule how many shows do I have to have at this theater in order to meet the demand that I'm expecting, and also where should I price the tickets so that I can make sure that I'm getting that demand that I expect. And if you run this in conjunction with, okay, now that I know that I'm going to be having $40 tickets and I'm expecting to sell 1,600 tickets, that will give me, I can actually multiply those together, that would make $64,000. You'd need to make sure that in order to make money, your costs are under that $64,000. So you can then use this information in conjunction with a cost and revenue model to determine where do you need to have your costs. And if your costs are going to be more than that, then you're going to either have to cut costs or you're going to have to figure something out to make this all work out. Are there any questions on this problem? Okay. Now, before I go to the next one, I do want to show you some trick in Desmos. So we have this, and this took us a long time to find this intersection here. If I click on one of the lines, you can see how a little gray point showed up. It will tell you, Desmos will tell you the exact intersection point. And you can see that it matches with what we visually read. This is really nice if it's going to be something with decimals. Of course, it's rounded. These came out to whole numbers, but sometimes you may have intersections that are decimal values. And Desmos can't give you the exact number, but it can give you a rounded number. And so you can click on it to verify the solution as well. But it's good practice to not do that so you can, practice reading the graph. Okay, so here's my last example. Sarah has 2 job offers for working in a beauty store and needs to decide which one is better. Job A pays $15 an hour. Job B is $7 an hour, but also pays 30% commission on, whatever she sells when she's working at that store. I did this because I go to Ulta a lot, and there are people who work in Ulta that there are some that are just general people that work there, just work for Ulta, and they get just paid per hour. But there are specialists that are there that work for the companies, and they get paid per hour, but then they also get paid off of commission. So so they're both working at Ulta, but they have 2 different positions, and they pay differently based off of what you're doing here. So this is a good example of, say you were applying to work at Ulta, and you have these 2 different jobs. You want to figure out kind of like, okay, which is the best one to take? Where am I going to be making the most money? And you have to do some estimation here, to figure out if it's feasible or not. You don't know, especially with commission, how much you're actually going to sell, but to see if it's reasonable or not. So anyway, assume that for both jobs, Sarah would be working 8 hours a day. So, let's just say 8-hour shifts. How much in sales would she need to do each day for the jobs to pay the same? So we're going to just look at how much would she have to sell in one day for job B to make as much as job A. That's what we're looking at here. We don't have to look at per day. We could look at per week. We could do per month, per year. But if I was in this situation, it would be really hard for me to quantify a reasonable amount of sales to make in a week. But looking at it per day, like I need to sell this much product today, on a per day basis, is a little bit easier to conceptualize and think about, is that reasonable or not? Versus if we said, well, how much do you have to sell in a year? I don't know how much is reasonable in a year. That's a huge number. I don't know. So we're going to figure out how much you might need to do each day for them to pay the same. And then based off of this, which job offer should she take and why? So we're going to have to do, there's no right answer to this. It's kind of based off of, you know, your assumptions and you know, how good you think your sales technique is and things like that. So we're not given any equations here. We need to write equations for job A and for job B. So job A just pays $15 an hour flat. So I'm going to just use A as my output. Actually, I'm going to use function notation here so that you guys get used to that. And I'll use a capital A. And actually, instead of X, let's see. How do I want to do this? Okay. I was going to do multiple variables, but I think that would be too complicated for you guys. So let's say, okay, so we've got job A, and then let's say our variable S is for the number of sales that we're doing. And so we're looking at this on a per day basis. So for job A, you get paid $15 an hour, and it does not depend on the sales that you're making at all. And we're going to do this on 1 day. So you're getting $15 an hour, and you're working for 8 hours that day. And sales are not part of it at all. So our equation is just basically, let me actually do this vertically. For job A, our equation, when I multiply 15 times 8, it's 120. So S, and I should say let S stand for sales in dollars, like how many dollars of sales you need to do. So for job A, it doesn't matter how many sales there are, you're not getting a part of your income. You're getting paid $120 per day. This is per day because I multiplied the hourly by the number of hours we're going to be working in a day, which is 8. So you're making $120 per day flat. It's constant. It doesn't change. So there's no variables in there. It's just going to be a horizontal line here for job A because it doesn't depend on your sales. Now job B does depend on sales. So we're going to call that B of S. And you get paid $7 an hour. We're going to be working for 8 hours. So we'll just multiply that by 8. Plus 30% of your sales. So 30%, we always write that as a decimal. So that's 0.30 of sales. Of always means multiply. We're multiplying that by the number of sales. So when I actually multiply this out, 7 times 8 is 56 plus 0.30S. So you have a base pay of $56 per day, which is much less than the $120, but you do have more money based off of the number of sales that you would do that day. So it's going to increase based off of the number of sales. So we have a positive slope. So we've got this equation going on here. Are there any questions on how I came up with these equations before I start graphing these?
Looks good. Thank you.
Okay. So that's probably going to be the trickiest thing out of this whole thing. So going back to Desmos. Now, if I do this, I think Desmos will assume that it's input. No, it's, well, maybe it doesn't. I'm just not in my, can I reset the view? Does that, nope. Okay, I'm going to just make a new blank graph so I start back at 0. Because okay, 120. Okay, so our value's up at 120 in the Y, so I definitely have to zoom out here to be able to see this. So I'm going to just zoom out. So even though I have S and we normally graph X or Y, because I put it in function notation, Desmos knows that S is the input and it knows how to graph it. So this just represents we've got a flat 120 that we get paid per day. my second equation for job B is 56 plus 0.30s. So you can see the intersection point here, and then this is one where you'd probably not want to kind of eyeball it because you see it didn't actually fall on one of the grids here. So this is where being able to click on it, and it doesn't matter which one you click on it, it will still give you the same point, but clicking allows you to see that break-even point. So our solution here to this system, if I hover over it, is 213.333, and that's probably repeating, comma 120. So I'm going to just go back over here. Our solution, 213.33, and that's our input, and it's in dollars, which we round to 2 decimal places because money, we always have 2 decimal places for cents. So that's 213.33, and then I've forgotten what the other number was. I'm going to go back 120. Okay. So that's our order pair. So this is, we need to know, well, what does this mean? So S is our input. This is our dollars of sales. And then the output is basically our income, making $120, because that's where we break even with job A, where you make that per day. So Sarah would have to sell, based off of this, or $213.33 worth of product. So I'm going to just put that on the next slide here. Sarah would need to sell $213.33 of product per day for the 2 jobs to pay the same, essentially. So the next part of the question is, based off of this, which job offer should she take and why? Now this is completely open-ended, and you can have total different, based off of your skills. Me spending a lot of money on makeup. One person can easily go into a store like Ulta and spend, depending on the brands you're buying, you could have one person spend that much money alone in one trip. So, you could say, look at that and say, oh, well, that's basically, if I can get one person to buy my stuff, I only have to get one person each day to buy my stuff. And, and I could probably, you might think to yourself, I can get more than one person to buy my stuff. And so then you might say, okay, I want the job with commission because I'd be able to make more money then. On the other hand, you can think of it and be like, well, they have to buy this specific brand. And when people go into Ulta, they don't usually just buy one brand. They maybe buy multiple brands. And so maybe they only buy one, and that product's about $30. So like, let's say we take 213.33 divided by 30. That comes out to 7.111 on my calculator. So that would be, I'd have to get maybe 7 items sold. If you're looking at like average price, you're like, okay, it's not maybe I need one person to buy this much. I need people to buy 7 items from this brand. Can I sell 7 items in one day? And think of it that way and say, okay, maybe not. Maybe I wouldn't be able to. I don't think I can sell 7 in one day. Maybe if they're higher end, it might be harder. If it's $30, you could probably do 7. But if the products, whatever brand it is that you might be working for, the products are more expensive, like $80, you might not be able to get 7 of those. You'd probably be harder to get sales. So you have to make these considerations to kind of, figure out, well, what's reasonable. Can I make that much in sales? If so, if I think I can meet that, if I can make more than that, then I should take the commission job. And you have to be aware in a situation like this that if there are days you don't make that minimum, you're going to make less than the other job that you could have potentially had, but you could potentially make more. If you think, well, I'm, not really good at selling, I don't know if I can do that, you might say, I just want to take the flat rate, the $15 per hour, and do job A because that's more consistent. This kind of consideration that we're doing here is really good if you're looking for a part-time job or even your full-time job, and you're, maybe you're working at a restaurant or something until you can get your degree, and you're in a job where instead of commission, maybe it's tips, and you have to kind of figure out, well, if my tips are about 20% of whatever the food is for that day, assuming people give a 20% tip. Okay, and now I have to figure out, well, how many, tables that I'm going to get that day, how much are they spending at each that, or maybe, you have to do all these calculations to kind of figure out, well, should I take the job at the restaurant, or should I take another job at Walmart where I don't have with that? I actually had a friend do this calculation. She could have gotten a job with just an hourly wage at like Walmart or something, but she actually chose to be a bartender because with the tips, she did the math and she did, based off of how much she thought she would get in tips and everything like that. And it actually came out better, even though the base pay is usually less for jobs like that because they expect you to make up the difference in tips. So this is a good example. Even if you're not in this situation, you might know somebody in this situation, or you never know, you might end up in this situation where you have to do some considerations like this. And it may have no relevance to your degree, but it might be relevant to your life. So that's basically how you can use a system. You can look at it graphically, find the solution, why, systems are important, how they come up in real life. It's one of those things about math that people don't realize how much doing this kind of math can be very helpful to them. So I'm off I'm very passionate about this, as you might be able to tell. This is the thing that I love because I see how useful it is, and being someone that I love numbers, it's like, well, you can do the math to see what is better. You don't have to guess and just go on gut feeling and everything like that. But do you guys have any questions?
No, but one factor is probably in this situation, you weren't counting on COVID. So I would go with the $15 an hour.
Exactly. That's the other thing. And nobody was counting on COVID this year. I mean, like, had I known that COVID was going to happen, I probably would have bought a lot of stocks in like GameStop, which now apparently is like making a lot of money right now.
Oh,
So
I can see that. Yeah.
But it's because, unfortunately, I didn't think like, oh, people are going to get home, play games and everything. I missed out on that. So
Yeah, that's too bad.
Yeah. So.
Yeah. Yep. There's always the if game, if only.
It is, yeah. There's a lot of things to consider in real life. If it was a perfect world, we can do this calculation, but we don't live in a perfect world. You just have to get estimates.
Right.